Hi everyone. This video is going to be an exciting one. This is the low noise amplifier that we constructed in the soldering with a solder stencil video, and it's also the one, as you might assume, that we did in the solder stencil video where we were experimenting with making a solder stencil. So what this is a 100 to 300 megahertz low noise amplifier made by, the chip is made by Skyworks. It's a 67015 low noise amplifier, and Skyworks has a series of amplifiers in this series that go from this one, which is 30 megahertz to 300 megahertz, but you can only get below 100 megahertz if you have a special input matching network, and that would overly limit the usefulness of this beyond sort of the 50-60 megahertz range. So I elected not to do that. Skyworks has a range of low noise amplifiers in this family. They have the 67015, which is the one that we're doing today, from 30 megahertz to 300, and they also have a 1.5 gigahertz to 3 gigahertz, a 300 megahertz to 600 megahertz, and a 600 megahertz to 1.5 gigahertz. The pinout is the same between all of these low noise amplifiers, I'm pretty sure. It's just the matching circuitry and passives that are different. So this breakout board will actually work across the range. Most useful to me is the 30 to 300 for at least the few projects I've got on the front burner. So that's the one I decided to construct. I've got these for sale on Tindy, and the first one has already been sold, and the characterization I'm going to do today in this video is actually going to go to that first customer. So it might be kind of fun for this first customer to know that all of these performance measurements were actually done on the one you got shipped. I will, of course, test all of them before they go out the door to make sure they meet basic specs, but this is going to be somewhat more in depth. Okay, so with that said, what exactly are we going to try to measure? Essentially what I'm going to do is start with this table, which is the normal operating characteristics in the datasheet, and go by one and compare observed results with the specifications, and hopefully they line up just perfectly. Okay, so we're going to get started with the measurement, and there's a couple of things that we need to check before we begin. For each one of these tables, usually prior conditions are listed, and so we need to verify that we're actually meeting these prior conditions to make sure that these values are going to represent what we expect. So we're looking for 3.3 volts and 18 milliamps. So in the power supply we have 3.3 volts and 18 milliamps about. So that's good. Ambient temperature is listed as 25 degrees C. It's probably not quite that hot in here, but that's fine. And we're expecting negative 20 dBm for the test. So we're going to set the tracking generator there to be 20 dBm, and it's still off because we don't have anything hooked up. Okay, so there's a couple of measurements that we're going to be doing. We will be attempting to measure noise figure, but we can't do that until we have gain. And also noise figure, especially a noise figure this low, is going to have its own complications. Okay, so small signal gain is expected to be 17.5 decibels at 250 megahertz. So before we begin, we actually need to normalize the tracking generator So we'll just put a coupler between our cables there, and for the purposes of this, we have to assume that this coupler is completely transparent, because essentially what we would like to do is normalize the tracking generator at the plane of this connector, right? But in practice, we can't exactly do that. So this coupler, you know, it's not a perfect measurement of the exact power at the end of this connector, but we just sort of have to accept it. I should say as a disclaimer, I'm definitely not a metrologist. I'm not, you know, I don't claim to know everything about doing high precision measurements, but, you know, I'll hack it anyway. Okay, so we're going to turn the tracking generator on, and to start with, you can see that it's right there at negative 20 dBm. That when I normalize it, it should go and be 0, and it is, right? But what I can do is update the reference position down, and then I can get a new 0. So you see that there's 0, but that's really, you know, negative 20 dBm. But for our intents and purposes, it's 0 relative to the power we're expecting. So I'm going to turn the tracking generator off, and then we'll put our amplifier in line and then turn it back on. And then when the amplifier is connected but powered off, we have, you know, this interesting trace. And what this means is that, you know, energy, RF energy, is leaking through the amplifier just based on the power of the signal, the input signal itself. You know, this is not powered. So that signal is just what's going through the traces, through the air, through the amplifier's transistor itself. And that, to me, is, you know, an interesting thing. So what I'll do is I'm actually just going to go ahead and save this trace and then move on to the next one. Okay, so now we're going to turn the amplifier on. Okay, so I just realized that I've got the amplifier hooked up backwards, so you can see the input to the amplifier is going to the output to the spectrum analyzer. The output of the amplifier is going to the tracking generator. And this is a strange thing to do, you know, on the face of it, but you can actually see that one of the parameters that we'll measure is reverse isolation, which is exactly the way it's connected now. It's connected backwards. And we're expecting 24 dB of isolation. So we should get, you know, the trace should be 24 dB down from the reference. So we turn the power on, we'll see that the trace actually goes down from it just being unpowered, but it's not quite 24 dB. You know, it's actually just under 20 or just more than 20 dB of isolation, and then it gets to be, well, remember that if we put a marker in here, the performance is only specified up to 300 megahertz. So it's 21 dB of isolation. That's, you know, it's not quite up to spec. Let's see. Yeah, it's not quite up to spec. It's about 3 dB shy of spec on reverse isolation, which is fine. I'm not, you know, really that concerned about that. So I'm going to go ahead and freeze that. Start up a new trace. Okay. And then I'm going to turn this off, turn the tracking generator off, and then flip it back around. Okay, so now the amplifier is still powered off, but connected with the tracking generator on. And it's interesting to see that the shape of the feed-through of when the amplifier is off is pretty close to the same shape as when it's installed backwards. So let's turn the amplifier on. Okay, and there's the performance curve we're looking for. and that's the forward power. Now, the small signal gain is supposed to be 17.5 dB at 250 megahertz. So let's move the cursor over. There's 250, and it's 17.35, and that's awfully darn close. You know, it's supposed to be between 15.5 and 17.5. So that's perfect. That's exactly what we're looking for. And I'm just going to write down these figures, and we'll move on to the next. Okay, the next thing I intend to measure is the 1 dB input compression point. It can be between -6 and 4 dBm, and what this is a measure of at what point do we start saturating the amplifier. So the way I have this set up is I actually have a zero span at 250 megahertz, so this width of the screen is all the same frequency. It's just basically looking in time. So I have it set up to deal with the maximum amplitude of signal, because you know we're going to be doing -4 on the input, and that's going to be +17, so that's plus 22, or sorry, that's +15 or so dB, and that's technically within the range of the analyzer, but I'm going to put the 20 dB attenuator on the input anyway, just as an extra measure of safety. So the tracking generator is still set to -20, and I'm just going to I'm going to step it up 1 dB at a time with a marker and see how quickly it keeps pace with what it's supposed to. So notice that with it 20, this is 21.9 or thereabouts. So we're looking at this number plus 1.9. So we can use that to keep track of when this number is plus 2.9. So whenever this is 2.9 away, we've reached the 1 dB compression point. So let's scoot ahead to 10. So that's still, a little over 1.9. Let's go to 5. So we're looking for 5, 6.9 or above. So we've actually reached the point of 1 dB compression at 5. So 7, we're looking for 8, 9.9. So 10.2 is pretty darn close to the 1 dB compression point. It basically is. So, I'm just going to call that, this is a very imprecise way of measuring it, but I'm just going to call that 7 dB. Which is, below the minimum, but I'm not completely convinced that I'm measuring that as accurately as it really deserves to be measured. I don't have the equipment to measure third order intercept points because I don't have another tone generator. So I just can't measure those. It's not possible. I'm not going to bother measuring output return loss. So the next one to do is noise figure. And this one can be a major pain. So to measure noise figure, it's highly dependent on the noise floor of the machine. And this is frankly not a really great spectrum analyzer. And its noise floor, and this is even cheating with a 10 Hz RBW and zero span. So this is the terminator, it's on the input, and I've got 10 averages going through, and you can see this purple line, that's currently the current trace. The yellow line is with the input open. So now what we need to do is take the terminator off of this, plug in the amplifier, and terminate it, and we will be able to see how much the noise of the signal goes up. Alright, so I'm here at work and I'm trying to do the noise figure measurement of the LNAs, and I decided to do it at work because it takes a really long time to scan these traces. In fact, it's been 20 minutes to get the reference trace of when I had the terminator here. So we're able to get negative 154 dB per hertz on that trace, and this purple trace is just with just an open cable, and so there's enough stray energy in the world and the environment coming in that we're looking at 10, 20, 25 hertz worth, or sorry, 25 dBs worth of energy. So there's really no chance that we'll be able to measure the noise figure of the amplifier, because by math, assuming we're even close, the noise figure should be down in this range, the trace will, with the amplifier terminated. But I'm going to plug it in, try it anyways, and we'll see what we get. Just for reference though, I'm going to capture this purple trace when I have this plugged in with the terminator but not powered. I'll capture a purple trace and then I'll power it and see what we get. So the only thing I can say conclusively is that I can't say anything conclusively. The LNA is hooked up with the 50 ohm load. It's powered, and the blue trace is with it powered, the magenta trace is with it unpowered, and the yellow trace is with the input of the spectrum analyzer terminated. So if you look at the Maxim application note that I learned about this method from, and I'll link it to the video, they show that this entire part of the section, or of the device under test, needs to be in a Faraday cage. And the reason for that's kind of obvious, right? I mean, if we're getting all of this stray signal, the purple is actually no different between having this just open and plugged into the amplifier. It still had this purple trace, and that's just the ambient RF energy in the air. So then the magenta trace actually seems like it improves that a little bit with the amplifier turned on and terminated, and I'm not really sure what the reason for that is. Maybe somebody can post in the comments better information, but one way or another, I know that the difference between these signals is dominated by just the ambient energy in the environment. And so I can say that the low noise amplifier has low enough noise that it doesn't contribute more to the input of the spectrum analyzer than just the ambient energy does. Other than that, I really can't say anything, and I'm not surprised. A high gain LNA, well, an LNA with a really low noise figure is going to be a difficult thing to measure without having the proper equipment, and I just don't. Okay. The next one that we're going to try and measure is input return loss. This one's kind of a difficult one to explain. And in fact, this is the third time that I've tried to to explain this one and shoot this video. So I'm going to start from scratch again. So the idea of input return loss is that we have some kind of a source. Okay? And that's going into some device. Okay? And then that device either is an antenna or an amplifier or whatever, it doesn't matter. It doesn't need to have any kind of an output port. So, what input return loss is it's how much of the signal is absorbed by the device under test. And by that I mean we measure it by measuring how much loss we get in the return reflected signal compared to a perfect reflector, be it a short or an open. And that's actually exactly the way we measure it. So we're going to use a directional coupler, and what these are is they're a special kind of device that has an input port and an output port, and then 1 or 2 coupled ports. And the coupled ports are often depicted like that. So as energy goes in one side of the directional coupler, that coupled energy will go out one of the coupled ports. And I'm pretty sure that's the way that it works as far as the directionality goes. And then reflected energy coming in the other port goes out the other coupled port. And so that's why it's called a directional coupler, is because we can actually get a sample of the energy going one direction versus the other. Now, as you might expect, this isn't a perfect measurement. And there's a measure called directivity, which is expressed in dB. And that is basically like, let's say energy going this way is primarily coupled to this port. Directivity is how much loss we expect to see on this port. So if we're sending 0 dBm through here, let's say we expect -40 on this port, and that would be 40 dB of directivity. I actually have a directional coupler that's constructed like this, and we can take a look at it. Okay, so this is a surplus cellular industry directional coupler. It's made for 800 megahertz. So the idea is power comes in this port, goes out this port, and then some of that input energy is sampled here on this -6 dB port. Now, that's the directional part. Input goes to output and 6 dB. But what about reflections? So reflections come in the output port and get coupled to this port and are absorbed by the 50 ohm load. So inside the directional coupler, we can see that its construction is actually pretty straightforward. This is again the input port, and there's the output port. And we can see that inside there are these 2 silver-plated shafts that are very closely spaced to one another. So it's just like the drawing I drew here, right? So energy comes in the input port, it couples to this shaft and comes out the coupled port. And that's, I ended up remembering this correctly, right? And then reflected energy comes in this port and then goes out and is absorbed by that. So if we want to measure how efficiently our device under test is accepting energy from the source, we can use a directional coupler with the intention of sampling that quantity. So in essence, we'll wire this up kind of backwards, in the sense that we'll use the input port connected to the device under test, the output port will be the signal source, and then the coupled port here, the 6 dB port, will be measuring the reflected energy. Okay, so we're not going to use this directional coupler because it's optimized for 800 megahertz. Instead, we're going to use this mini circuits one, which has a much broader band. But it's I think this one works with the transformer. But we're going to wire it up to the spectrum analyzer, and then I'll be able to show you how to measure things like its directivity and also its coupling parameters. Alright, so the first thing we'll do is measure the coupling, the level of coupling between the input and the coupled port. So the input is hooked up to the tracking generator, and the coupled output is hooked up to the input of the spectrum analyzer. Before we get started, I'm actually going to hook up the tracking generator to the spectrum analyzer and normalize the tracking generator. We can see that this is the normalized trace. I went ahead and did that normalization I talked about. And all but 10 dB of the energy coming out of coming into the input port is leaving the coupled port. So we can save this trace, and we can call that trace basically full power going into the input. So we'll go trace 1. Let's get 10 averages just to make it smooth. Okay, so now that we've got our top end reference trace, we're going to reverse the connection of the input and output and do it again, and that will give us our directivity. So now with the connections reversed, our second trace here is the directivity. So we can see that there's about a 30 dB difference at, I think that's 150 megahertz, and then by the time it gets to, what is that, almost a little over a gigahertz, we've got 20 dB of directivity. So most of our measurements are going to be in this range. So as long as the input return loss is less than 25 or so, we should be able to measure it just fine. So now what we do is on the input, we'll take off this terminator. Okay. And then we can see that purple trace is moving. I'm going to turn off these just so we know exactly what we're dealing with. Okay, so we can see that the reflection coming off of that unterminated port is almost exactly the same. It's darn near when the coupler was in the other direction. So that open port is reflecting almost all of the RF energy, which is basically what we expect, right? Okay, so I'm going to put this back on really quick and save that purple trace. Okay. So with the amplifier connected, terminated, and on, we can see that the input return loss is actually really good at that low point there. So let's find out what that is. Let's see. There we go. Okay. So that low point looks to be about 36 dB. That's pretty good. But remember, we're measuring everything at 250 megahertz, so let's go to 250. Okay, and what we really need is to know the difference. So let's turn on marker 2. We're going to put it on trace 1 at 250. Okay. Marker 1 needs to be exactly 250. Okay. And then we'll clear that and turn on the table. Okay. So we're looking at negative 26 dB minus 11 dB. Can look at the input return loss, and 17 is typical. And we measured 15. So, you know, we're not too far out. So we're all finished. I have made an attempt to measure every one of these parameters. there's one obvious and notable exception, and that's the noise figure. And I think I showed quite conclusively why we're not able to get that measurement. It'd be nice to have a Faraday cage, but I don't. So we're just going to have to accept that it's not, you know, shockingly terrible of a noise figure. I have every reason to expect that it's probably in reality close to the published spec. And the reason I say that is because that is very close to the published spec. That is very close to the published spec. That is very close to the published spec. That one is a little bit worse than the published spec, just a smidge. But I'm also not very confident in the measurement methodology of this one. And then these are right on the published spec. So I have every reason to believe that the noise figure as well is along with the spec. So I think that's going to be it for this video. Overall, I'm really happy with how this project has gone. I've had a lot of fun doing the stencils and doing stencil-based reflow soldering. That's the way to go. There's really no better way to solder than with a stencil. So like I mentioned at the beginning, this is the 100 megahertz to 300 megahertz version of the PCB. I've made quite a few of them just because I had the parts. So some of them are up on Tindy if you want one. I'm probably going to make the other models. So I've ordered the chips and the capacives for all of those different models, and I will do a similar video to this for each. Obviously not as heavy on the explanations because, you know, I've already explained them, so I'll just sort of go through and measure them. But I'll probably make those available for sale as well. If you just want a PCB, I'll put a link to the dirty PCBs. I've published this on there in case you just want to click and get some PCBs on your own. So that's an option too if you just want to solder them yourself. Well, I hope you've enjoyed this, and you know, I definitely accept and admit that I'm not, you know, a metrologist, right? This kind of measurement, detailed measurement, is not my biggest skill. So I encourage anybody who knows more than I do to chime in the comments and mention the things that I did wrong. I hope this was maybe helpful to others. So as always, thanks for watching. Thumbs up and subscribe if you enjoyed this, and there should be many more to come. Thanks again.